Imagine a triangle drawn on a sheet of paper. Pick the sheet up and turn it. The triangle swings around, but nothing about its shape changes. Every side is the same length. Every angle, the same angle. That is a rigid motion, a turn or a flip in a mirror with no stretching or squashing. Watch it rotate. Trade the triangle for two arrows, a green one and a blue one. Each has its own length, with a definite angle between them. Certain special matrices do exactly this to vectors, moving them, yet leaving every length and angle untouched. Rotate the picture. The arrows keep their sizes, and the wedge between them never opens or closes. Those are the orthogonal matrices, the subject of this lesson. To build orthogonal matrices, start one level down with orthogonal vectors. Two ideas do all the work: the dot product and the length. That gives three definitions. Two vectors are orthogonal, perpendicular when their dot product is 0. A vector is a unit vector when its length is 1. And a set is orthonormal when it has both at once, every vector length 1 and different ones perpendicular. Hold on to that word, orthonormal. Here is the leap. Take a square matrix Q and read it column by column, Q1, Q2, and so on. We ask one question of those columns. Are the columns orthonormal, each of length 1, and mutually perpendicular? When both hold, Q is an orthogonal matrix. Picture it. Here are two columns of a 2 by 2 orthogonal matrix as arrows. Each reaches length exactly 1, landing on the unit circle, and they meet at a perfect right angle. So their dot product is 0. Length 1, mutually perpendicular. The whole condition, right in front of you. Why does that condition deserve its own name? Look at Q transpose times Q. Its entry in row I. Column J is exactly the dot product of column I. With column J on the diagonal, a column is dotted with itself. Length squared 1. Off the diagonal, different columns are perpendicular. So it is 0. Once down the diagonal, 0s elsewhere. The identity matrix. So the whole condition collapses into one clean statement. A square matrix Q is orthogonal if and only if Q transpose times Q equals the identity. Whenever you test a matrix, this is the line to reach for. Now the payoffs roll in, and the first is almost a gift. From Q transpose, Q equals I. Q transpose is an inverse for Q. And for a square matrix, that is all it takes. The inverse of Q is simply Q transpose. No elimination, no cofactors, just flip it across the diagonal. And since an inverse works from either side, Q times Q transpose is the identity too. So the rows of Q are orthonormal as well. Perfectly symmetric. Here is the promise the hook made, now proved. Take any vector x and hit it with Q. Its length squared is Qx, transposed, times Qx. Slide the transpose inside. That gives x transpose Q times x. But Q transpose Q is the identity. It quietly vanishes, leaving x transpose x, the length of x squared. So the length of Qx equals the length of x, always. Lengths are preserved. Angles are the same story. Run the identical trick on Qx dotted with Qy, and again, Q transpose Q disappears, leaving x dot y unchanged, and the angle is defined through that dot product. If the dot product and the lengths are untouched, the cosine of the angle is untouched, so the angle cannot move. Q is a rigid motion, a rotation, or a reflection, never a stretch. Let's watch a rigid motion in 3 dimensions, where reflections show themselves. Here are the 3 axes at the origin. Take a vector reaching up into space with some length. Now reflect the whole world in the floor. The plane where z is 0. The z coordinate flips sign and the arrow drops below the floor, a mirror image. But measure it. The reflected arrow is exactly as long as the original. That mirror flip is exactly what the matrix diagonal 1, 1, minus 1 does. A genuine orthogonal matrix. Rotations and reflections in any dimension are the orthogonal matrices. One more number falls out for free, the determinant. Take determinants of both sides of Q transpose Q equals I. The determinant of a product is the product of determinants, and a transpose keeps the same determinant. So this becomes det Q times det Q equals 1. That is det Q squared equals 1. So the determinant of an orthogonal matrix is either plus 1 or minus 1. Never anything else. And the sign carries meaning. Plus 1 is a pure rotation, a clean turn, no mirror. Minus 1 means a reflection is baked in, flipping the world's handedness. Both perfectly rigid in two flavors. Time to make it concrete. Is this matrix orthogonal? 1 over root 2 times 1? 1 minus 1, 1. Let's run the checklist. First, the column lengths. Column 1, 1 and minus 1 over root 2 has length squared a half times 1 plus 1. That is 1. Column 2 gives 1, 2. Both are unit vectors. Next, are the columns perpendicular? Their dot product is a half times 1 minus 1, 0. So the columns are orthonormal and Q is orthogonal. Cross-check the other way. Multiply Q transpose by Q directly. The diagonal entries are 2, the off-diagonal 0, and the half out front makes it the identity. And see length preservation live. Feed in x equals to 0 of length 2. Q sends it to 1 over root 2 times 2 minus 2. Its length squared is 4 over 2 plus 4 over 2, 4. So the length of Qx is 2, exactly what we started with. Moved, not stretched. A second example, a reflection. This matrix keeps the first two coordinates and flips the third, mirroring space in the xy plane. This one is symmetric. So Q transpose equals Q. Then Q transpose Q is just Q squared. Squaring the diagonal gives 1, 1, 1. The identity. So Q is orthogonal. Now the determinant. It is diagonal. So multiply the diagonal. 1 times minus 1 is minus 1. That minus sign is the tell. This orthogonal matrix contains a reflection. Across the plane z equals 0. Its eigenvalues read straight off. Vectors in the xy plane are untouched, so lambda is 1. Vectors along the z-axis flip, so lambda is minus 1. Both have size 1, true of every orthogonal matrix. And a quick numeric check. Two vectors A and B have dot product 1. Reflect both. The third coordinate flips, and their dot product is still 1. Same dot product, same lengths, so the angle is perfectly preserved. Your turn. Here is a 3 by 3 matrix, 1/3 out front. Pause and decide whether it is orthogonal. Check that every column has length 1, and the columns are mutually perpendicular. I'll wait. Here is the walkthrough. Read the columns downward. Column 1, 2, 1, 2, has length squared 1/9 times. 4 plus 1 plus 4, 1. Columns 2 and 3, the same. Every column is a unit vector. Now the three pairs. Column 1 dotted with 2 is 1/9 times minus 4 plus 2 plus 2, 0. 1 with 3 and 2 with 3, also 0. Every pair is perpendicular. Unit columns, mutually perpendicular, so Q transpose Q is the identity, and Q is orthogonal. If you got that, you have truly got this. Trap 1. Confusing the two orthogonals. Two vectors with dot product 0 are orthogonal, yes, but that alone does not make a matrix orthogonal. It must be square, with orthonormal columns, not merely perpendicular ones. Trap 2. Forgetting unit length. Perpendicular columns are only half the job. If a column has length other than 1, Q transpose Q is diagonal, but not the identity. Both must hold. Trap 3. Mixing it up with skew-symmetric. Q transpose equals minus Q is a different thing entirely. Orthogonal always means Q transpose. Q equals the identity. Trap 4. Assuming the eigenvalues are real. All you truly know is that every eigenvalue has size 1. For a real rotation in the plane, they are complex. Cosine theta plus or minus I sine theta on the unit circle of the real line. Let's lock it in. A square matrix is orthogonal exactly when its columns are orthonormal. The same as Q transpose Q equals I. Its inverse costs nothing. Just transpose it. Q inverse equals Q transpose. It is a rigid motion, preserving every length and angle, because Q transpose, Q quietly cancels inside the algebra, and its two fingerprints. The determinant is plus or minus 1, rotation or reflection, and every eigenvalue has size 1. Hold those 4 lines, and orthogonal matrices will never puzzle you.